This morning, we talked about creating VLANs, virtual local area networks, and creating multiple broadcast domains. Then we had a problem. Now that we've got all these VLANs created, we got to figure out a way to make them talk to each other. And the router on a stick, and the reason it's called that, because if you look at the image at the bottom, it looks like there's a router on a stick, is one of the ways to do that. We're going to look at it as well as the switch virtual interfaces, SVI, which is used in a layer 3 switch. I'm going to try to do demos with each of these, and then we'll look at, actually do the router on a stick, and then we'll look at the bullets here on this thing. So on the router on the stick, the first thing that has to happen, as we talked about, to get from this switch to the second switch, we have to have a trunk port. So if I go in here and look at the show interface trunk command, we do have a trunk port. The other one that has to be a trunk port is this one, because it still has to carry all of the information up here to the router. So let me go ahead and gig 01. Let's go ahead and make it a trunk port before I forget to do that. Config T, and then it was interface with gig 0/1 switch port mode trunk. This looks kind of different than what we saw earlier, because we're now going to and nothing happened yet, and because we're now going to a router. To make this work, we're going to use sub interfaces to do this. And this is connected to, I think, gig 01, gig or 00. So we will go into the interface gigabit 00, configure terminal, and interface gig 0/0. And now we're going to create sub interfaces. So interface gig 0/0, 0/0.20. Now I am in, you see, the sub interface configuration mode. So now what can we do here? One of the things we can do here is encapsulation. We're going to use our tagging encapsulation. So encapsulation .1q. The other thing, the question mark here, that we have to tell it is which of the VLANs it's associated with, and this one is going to be 20. Did I do, yeah, interface.20. So interface 20, again, keeping the VLAN number, the subnet ID, and the interfaces, in this case, all the same. Makes it a little bit easier to troubleshoot if we have to do something with it. Now we need to give it an IP address of 192.168.20.1, and we have to do the subnet mask. And now let's go up one. We need to do the same thing again with the next VLAN, gigabit 0/0.30, and we'll do encapsulation .1q, and this is going to be VLAN 30, and the IP address 192.168.30.1. I use the .1 addresses because that's the kind of the convention. There's no specification as to what has to be the default gateway, but the devices are configured with that as the default gateway. Then we have one more, gigabit 0/0.40, encapsulation .1q, 802.1q, and the VLAN number is 40 on this one, so the IP address will be 192.168.40.1. Subnet mask. If we show the IP interface brief, we have these things, but gig 00 is down and all these are down. What we should be able to do is to go into the config mode and interface gig 0/0 and give the physical interface the no shutdown command. show IP interface brief, and it will bring those up. Out of curiosity, can you run the DHCP server on subinterfaces? No, because you have to have specific protocols. In this case, .1Q. Well, if you run frame relay, you could. Frame relay and the 802.1Q are the protocols that would run on subinterfaces. You can't just, if I did that, and you can try it out. Let's go and see. Let's go to config T interface gig 0/1.10, and then I do an IP address 192.168. Let's try 100.1 255.255.255.0. And then it says configure IP routing on a LAN subinterface is only allowed if that subinterface is already configured as a part of 802.10, 802.1Q, or ISL VLAN. So in the question, can we run the DHCP server on it? Only if we have it configured on these interfaces. So you could, if that DHCP server was in one of the VLANs, the 802.1Q VLANs, it would be part of that encapsulation protocol, and we could do it that way. Frame relay also uses subinterfaces. I hope that answers the question. Though he said it did. At end. What the and Mike talked about this morning about the no IP domain lookup. When we give the no IP domain lookup command, if I make a typo, a lot of times it will do this. It's trying to resolve this to an FQDN, to an IP address. Control Shift 6, Control and the Shift and the 6 simultaneously is the break. It's like the Control C in DOS. Config T, and let's do the no IP domain. No IP domain lookup. And then let's try that again. It just says unknown command. So it prevents the IP lookup, the DNS resolution of these things. So let's go. Let's see where we show IP interface brief. So we have all of these things up now, and let's see if our trunk port here is a trunk port, because we need it to be a trunk port in order to be able to do those. Oh, golly, now that we've got the encapsulation protocol on the other end, the 802.1Q, which is already on this end, and it associated with VLANs, we're in business. So we should now be able to communicate from one VLAN to the other. What I like to do, this is the 40 VLAN. I like to start out in doing the troubleshooting the way that we talked about it. So first we would ping 127.0.0.1, the loop back, and we're in good shape there. And IP config, and I forgot what its address is, and ping its address 192.168.40.2, and we're in good shape. And now let's ping the default gateway 40.1, and we're in good shape. Let's go to the other end. Let's try one of the other ones. Let's try 30.1, which would be the default gateway. Hey, we're getting across. We're getting routing going on here. One of the other addresses, I can get this down here. Well, we got probably 20.2. Let's see what the maybe see what the address is on one of these other guys. So 20.10. I would have messed myself up, wouldn't I? 20.4, 20.10, 20.4. So let's see, and they're on different ones, 20.10 and 20.4. Let's see if we can get to those. So we ping. Yeah. Let's try 20.10. And sometimes these things take a few seconds to wake up in the simulator. Okay, we're in business there, the 20.10, and what was the other one, 20.2, I think. And again, maybe take a few seconds for this thing to wake up. So we're in business. We have connectivity among our different broadcast networks through this router on a stick. And again, a router on a stick because it looks like a stick sticking out from the switch. And that's why they named it that way. So the slides here say the router on a stick is one of the methods for inter-VLAN routing. A type of router configuration allows a single physical interface to route traffic between multiple VLANs on the network. Because we can use the sub-interfaces, because that was one of the protocols that was allowed as our VLAN tagging protocol. Router interface is configured to function as a trunk link. We put the trunk command on the switch, and then we put the encapsulation protocol on each of the sub-interfaces, which made it a trunk port. Trunk port allows all of the VLANs to travel on it. Performed by accepting the VLAN tag traffic on the trunk interface that's coming from the adjacent switch and internally routing between the VLANs using the sub-interfaces. So it is internally routing. They go up and down the same interface. You know, no big deal. I think we hopefully overcame that when we were talking about trunk ports and allowing the traffic from all of the devices. And if we got a trunk port, these things connected, it's two-way, it's full duplex. We've talked about that before. A router has an IP address on each subnet with one subnet per VLAN. No IP address on the physical interface, but the physical interface controls the up-down of these things. Adds the match subnet. When we did the encapsulation protocol, we had to specify which VLAN, which meant which subnet that interface was associated with. So router on a stick, a handy way to communicate between these things. The other method is the switched virtual interface. And let me see if I can get that one up and we can look at it. It's quite a bit simpler to configure than the router on a stick. Requires a layer 3 switch. I was doing it this one. It looks too much like a router on a switch. So let's just go down here and look at this thing. We're still waiting for a spanning tree. It's going to take us about a minute to get these things going, but we can do some of the configurations while we're looking at it. And in this one, I've only got 2 VLANs on it. We can show VLAN. And in the VLANs, we have VLAN 2 and VLAN 3. These, and again, the VLAN 2, the .2 network, VLAN 3, the .3 network. And the devices are, we put the ports of the devices onto the VLAN itself. So we're up here. Again, we need a trunk port between the 2 switches. So let's see if we have that interface trunk. Hopefully we do. Big T, one of the things you got to remember to do, but layer 3 switches by default are not configured to route. So we have to turn on IP routing. And that's just a matter of doing IP routing. And now we're going to configure virtual interfaces on this thing. So we interface VLAN 2 for the .2 network. And it says, hey, the interface came right up, change state to up. And it will do an IP address of get my fingers on the right key, 192.168.2.1, 255.255.255.0, and then interface VLAN 3 for the .3 network, and its IP address will be 192.168.2.1. 3.1, 255.255.255.0, and I think I got those right. And let's do a show IP interface brief on this one, and we get down to the bottom. We have them and they're in up. We talked about that. We want them to be in the up state. So again, let's try to see. Let's go here right from this side. This is the 2 network. Let's see if we can get to its default gateway, ping 192.168.2.1. And golly, we can. That's a good sign. Sometimes they're not this fast. 3.1, we can get there. So now let's see if we can get to something on the other side. 3.2 would be one of the addresses that would be available there. 3.2, and again, sometimes it takes a little bit of time for these to happen, for these to actually work out. So we're getting there. The request timed out. In Cisco, the first time you go to some place, you'll probably get a didn't work. And you'll probably get a didn't work because it takes some time for ARP to do the resolution. It comes up to the next ping packet before the ARP resolution actually takes place, and it has the MAC address available to it. So switch virtual interfaces instead of using the external router. As long as we're using a layer 3 or multi-layer switch, we can configure those things. Multi-layer switch, turn on IP routing, create the virtual interfaces to allow the devices to communicate with each other. We can have as many as we want. The one trick is, and I messed this up a couple of times, is because when we talk about the trunk port, show interface trunk, we could go in here and create these virtual interfaces. These VLANs need to be here so that the traffic from the VLANs can go through the trunk or allowed on the trunk. So regardless of this one, we had the ports on it, but regardless of whether you have anything assigned on the port or not, the VLANs need to be configured on the switch to allow the traffic into the trunk, into and out of the trunk port. So we have those. Layer 3 switch, communicate with the other layer 3 interfaces, eliminates the need for having a separate physical router, again, as long as we have layer 3 switches to do this. There are a number of labs distributed through here. Again, what I want to do is go ahead and keep going and then do the labs at the end, because we stop 15 minutes here, 15 minutes there. And to get the simulator going, it's probably going to take about as much time, as some of these are 5 minutes, about as much time to try to get it going as it does to do the lab. Consolidate them at the end. There's about an hour's worth of labs in this section. So the route statement, and the route print statement is a Microsoft term. Let me get the command prompt up here. If you've never done this, your computer has a route table in it. Route print, whole bunch of routes here, IPv6, and you notice that these are the link local IPv6 addresses. Let's go up here and find active routes, IPv4 route table. The default route 0.0.0 with a net mask of 0.0.0, same thing that we did on the router, 192.168.1.1. The interface that it goes out to get to that gateway is 1.27, which is the IP address of this computer. So a number of other things that are available here. The other devices that are on the local network, well, no, these are not on the local network. These are the virtual interfaces that would be there. So it has routes for all of the interfaces. We have some multicasts. We have some broadcasts. So route tables, the route print command allows you to see the route table that's on your individual computer. Specific route, the route statement helps us determine the specific router, if any, that's used for an outgoing packet. The specific local network used to send the packet, and the default routes with the gateway device is inactive. 3 basic types, and this is another one of the, I didn't really have to somebody tell me this, but we can have routes to the host route to a particular remote host if we want to go there. It's just a matter of how we mask the route with the, the IP route, the network address and the subnet mask. If we mask it with a 32-bit address, or a 32-bit subnet mask, we're going to go to an individual host when we do those things. We can go to a network or a subnet. IP route 192.168.1.0.255.255.255.0, and then whatever the next hop is going to tell us how to get to a network. If we have something smaller, it also could be a subnet. The default route, we've talked about that probably beating it into submission, but default route, when nothing else is available, we'll use the default route. The IP route 0.0.0.0 with a subnet mask of 0.0.0.0, and then whatever the next hop is. Can't find a route in the route table, then we're going to use it. Also called the gateway of last resort. The last resort is I didn't find a route. My last resort is to go to this other place and hopefully it can find a route for me. If it can't, then, and it doesn't have a default gateway or a default route, eventually we're going to get someplace that we can't go any further, and then we'll get, if it can't find anything, we'll get the error message, the ICMP error message back that the network, that we can't get to that network. This is something that you may want to do, the floating static. This is a static route that backs up a dynamic route. Now, think back to the administrative distance. The static route administrative distance was 1. The best dynamic routing protocol administrative distance was 90. So if you do this, you've got to set the administrative distance above what the routing protocol is that you're using. So if we were using EIGRP with a 90, we may set it at 100 or 95 or whatever we wanted it to be, so that it didn't take over from the dynamic routing protocol. This is a backup. Something happens to the dynamic routing protocol, the static is there, the floating static is there available to take over. Back up a dynamic route. Static routing on IPv6, and the objectives kind of, I think, overstate what this is right here. But before you configure the router with a static route, you have to enable the forwarding of IPv6, and you do. By default, the routers still are IPv4. IPv6 unicast routing turns on the ability to route IPv6 packets. IPv6 route command, not IP route, IPv6 route. And then when we want to look at it, show IPv6, we have to specify IPv6 for everything that we do in this thing. To show IP, or the IPv6 route command, global configuration mode, show IPv6 route static command, show IPv6 route static detail. We'll see different amounts of information in each of those. But I guess the key to take away from here is when we use IPv6 in routing, first we got to turn it on. And then when we do anything with it, we have to specify IPv6 as the protocol that we're using. The types of static routes, and this is another one that's kind of goes into the, yeah, we could do this, but maybe to make some good test questions, I guess. But 3 types of static routes. The directly attached static routes, created by specifying only the outgoing interface. We did that in the one that one of the statics we did a little earlier. We just specified the interface that's going out. The packet destination is the next hop address because the destination is assumed to be directly attached to this interface. And it should be. If you go out an interface from one router to the other router, then that's what we're going to be able to do. Let's use this one here. If we have these 2 routers connected, and this is gig 00, and that's a really good one, isn't it? Gig 00, and this is 192.168.1.6. let's try gig 0, 0. If we tell it to go out gig 0, 0, it's kind of like getting in a tunnel and going under the river or one of the any of the tunnels in the interstate. Once you're in the tunnel, that's where you're going. You're going to go to the other end of the tunnel. Once you go out that interface, you're going to go to the other end, and the other end is going to be the next hop address. So this one, we just specify the interface that's going out. Recursive is created by specifying only the next hop with the output interface being derived from the next hop. Yeah, it knows what it is. So in this one, we just specify the next hop IP address. The fully specified is we talk about the next hop address as well as the interface that it goes out of. We specify both of them. So kind of it said it's something to know, but it's something that, yeah, you could probably figure that one out on your own. Another little lab set here to do these things. And then we have the summary slide. So we talked about in this lesson, in this section, the routing protocols, the metrics. Each of the routing protocols use different metrics, evaluate the path they're going to take. What's the best path to travel to get from one location to the other? Each of them, again, use very different metrics. RIP hop count, it doesn't care anything about speed. OSPF is cost, and then EIGRP it's a hybrid metric. It really uses bandwidth and delay to do its calculations. There's a whole bunch of elements in there, but when you look at all of the calculation it does, bandwidth and delay is what it uses to do that. And the bandwidth is the lowest bandwidth between it and wherever it's going to. Information depends on the routing algorithm. Static routes manually configured. We go in and type them, IP route, wherever we're going to go to, next hop address, or the interface that's going out, or both. Dynamic routing protocols, the network adjusts the path automatically. Something changes, the routing protocol updates the path that we're going to go through. And RIP, 4 basic components: the routing update process, the RIP routing metrics, routing stability, and then the routing timers. A whole bunch of things that are available there to keep it within the autonomous system, the area that we own, as well as to prevent routing loops and to prevent wrong information. The split horizon things can't come back. Prefix length, the /, shorthand way of expressing the subnet mask. It tells us how many ones are in the subnet mask. Administrative distance tells us how reliable a routing protocol is, or how trustworthy a routing protocol is, in order to select the best path when there are 2 or more different routes to the same destination from different routing protocols. So if we had RIP and OSPF and EIGRP, RIP 120, OSPF 110, EIGRP 90, the EIGRP route's going to be the only one that will show in the route table. The others will still be available. If EIGRP went down, they could take over for OSPF would be the next one to take over the routing duties for these things. Metrics associated with the specific routes rank the most preferred to the least preferred. How are we going to get there? Gateway of last resort, the default route. Unroutable packets are sent there. If we have a packet that we don't have a route to, then we use the default gateway in order to get it to go someplace. So